We are Alexa, Piper, and Rebecca, and we're going to be presenting on the group 17 elements. The group 17 elements are also known as the halogens, and they are highlighted here in purple. I will be talking about trends for the properties of halogens. Looking at some of the trends in the halogens, we see that generally molecular size, density, boiling point, and melting point increase down the group, while the properties ionization energy, electronegativity, reactivity, and electron affinity increase up the group. These are the general trends of group 17. Some slight exceptions to these trends are made, such as the electron affinity trend. Shows that fluorine's electron affinity is 328 kilojoules per mole and chlorine's is 349 kilojoules per mole. While the rest of the elements in this group follow the trend of increasing electron affinity up the group, fluorine has a slight exception. Okay, looking at the general periodic trends where group 17 is highlighted in purple, the blue arrow increasing towards group 18 shows the general trends of electronegativity, ionization energy, electron affinity, and nonmetallic character, while the green arrow that increases towards group 1 shows the general trend for atomic radius and metallic character. When comparing trends of different groups to group 17, we see that closer groups such as group 16 follow some of the same general trends. Here we are only looking at elements highlighted in purple. Group 17 elements have higher ionization energies, electron affinities, and electronegativities than group 16 elements in the same period, following the periodic trends from the previous slide. We can also see that the trends boiling point, melting point, electronegativity, electron affinity, and ionization energy are followed in the same direction by both group 16 and 17. When looking at a farther group, such as group 1, we see that when looking at elements highlighted in purple, that melting point and boiling point do not follow the same trends as group 17. Melting and boiling point generally increase up group 1, but down group 17. Group 17 elements still have higher ionization energies, electron affinities, and electronegativities than group 1 elements in the same period, which follow the periodic trends.
So to begin a conversation about the general reactivity of the halogens, generally all neutral halogens are diatomic and are readily reduced into halide ions. And they actually have very high electron affinities, as discussed earlier, and this allows them to easily acquire an electron and be stabilized after they acquire this electron. And once they acquire one, they actually have a noble gas electronic configuration since they are the neighbors to the noble gases. And these diatomic halogens will combine to form gases that are strong acids in solution, with the exception of hydrofluoric acid, which will be discussed later. The halogens are also generally excellent oxidizing agents due to this electronegativity and high electron affinity. They easily accept and will be stabilized by accepting an electron, which will in turn oxidize the donating species. In particular, diatomic fluorine is the best and strongest oxidizing agent. In terms of specific reactivities for the diatomic halogens, diatomic fluorine is extremely high in reactivity due to its low bond association energy. And this is presumed to be due to the fact that even though fluorine does not have a particularly large atomic radius, it does have a significant amount of repulsion between non-bonding electron pairs. This actually creates a longer equilibrium bond distance, which makes the bond easier to break, and also due to the extreme electron-electron repulsion. In terms of diatomic iodine will react with its own ion, I- to form an ion complex, I3-, and it also will dimerize to produce I3+, I5+, and I2+. And this is mainly due to its large ionic and atomic radius as an element that is further down in the group. And the different iodine compounds that can form through these dimers reactions are seen in the right here on the image on top, where we see not only the different iodine compounds that were just mentioned earlier, but also the difference in bond lengths between the iodines in these compounds. And we can see that not only are they very large bond lengths, but they also vary from atom to atom. Lastly, diatomic chlorine is actually very thermodynamically favorable in terms of redox potentials, and the reaction between chlorine gas and different hydroxides will often be used to create things like hypochlorite, chlorite, perchlorate, and this can be seen in the image on the right, where we can see that there is a linear relationship between the redox potential and the reaction of chloride with different hydroxides to form different compounds. In particular, the perchlorate compound has a very high redox potential. In terms of specific reactivities for the hydrohalic acids, as mentioned earlier, HCl, HBr, and HI are all strong acids and dissociate in water into their constituent ions. In terms of their specific strength, hydroiodic acid is the strongest, followed by hydrobromic acid and hydrochloric acid. And then, of course, hydrofluoric acid is the weakest. And this is actually presumed to be due to the long bond length of hydrofluoric acid and the fact that it won't dissociate into singular F- ions like these other acids when placed into the water or solvent. This is actually because of the strong hydrogen bonding that occurs between F- and the hydronium ion. And it forms an ion pair F- coordinated onto H3O3+ in water. And the formation of this ion pair will actually reduce the activity of the hydronium ion in solution, reducing the strength of the acid. And so as the concentration of hydrofluoric acid increases, its tendency to form these hydronium ions increases, and the result is a reaction of this ion pair with hydrofluoric acid to produce another hydronium ion, and then this HF2- ion. We can also discuss the specific reactivities of the interhalogens. And the halogens will actually react together to form interhalogen compounds. And the way they react and the products they produce is dependent on the size of the central atom. And we can see this exemplified in the fact that iodine can actually have up to 7 fluorine atoms in a neutral molecule, but chloride and bromine have a maximum of 5 fluorine atoms that can be coordinated onto it to create a neutral molecule. This is also proven by the fact that iodine, to form any ionic compound or neutral compound, can hold up to 8 fluorine atoms. And this is again due to its extreme size and radius, so it can easily accommodate up to 8 fluorine atoms.
Now we're going to talk about some of the important chemical reactions that halogens participate in. To begin, metal halides can be formed through the direct reaction of a metal and a halogen. However, that process is pretty thermodynamically unfavorable, so instead, you'll often see metal halides formed through the reaction of a metal oxide, metal hydroxide, or metal carbonate with a halogen acid. In the example on the right, we see hydrochloric acid reacting with lithium oxide to produce lithium chloride. We can then also look at how the hydrochloric acid is formed. Hydrogen halides are formed through the direct reaction of hydrogen and a halogen. Here we see halogen gas and chlorine gas reacting to produce that hydrochloric acid. And although this is an inorganic chemistry course, we can also take a look at organic halides, many of which are formed synthetically and then can be used in the synthesis of many other organic compounds. This example on the right is of the bromination of benzene under the conditions of ferric bromide. Next, we can look again at some interhalogens, which we previously defined as a compound containing 2 or more different halogens. These species can be made through direct reaction, typically at high temperatures, such as the formation of chlorine monofluoride, shown here. However, they can also be formed through reactions with metal halides, such as the reaction of iodine with silver fluoride to produce iodine monofluoride and silver iodine. These interhalogens can also serve as intermediates in chemical reactions when larger, more complex interhalogens are being formed. If we look back at the first reaction on this slide, that produce chlorine monofluoride, we can further react this species with fluorine to produce chlorine trifluoride. Finally, we see that many interhalogens undergo autoionization as liquids, which makes them excellent candidates for non-aqueous solvents. With our understanding of the reactivities of halogens, we can now take a look at some real-life applications of these compounds. You most likely use chlorinated compounds to clean much of your belongings, and you can also use chlorine to disinfect water in swimming pools. Chlorine dioxide is a particularly powerful chemical to kill pathogenic microorganisms and was used to clean congressional mail that may have been infected with anthrax. You also should use fluorine every day to clean your teeth with toothpaste. Common fluoride compounds are stannous fluoride, which is tin 2 fluoride, and sodium fluoride. And lastly, if you know anything about green chemistry, you're likely very aware of the Montreal Protocol, which initiated the phase out of chlorofluorocarbons, which are also called CFCs. These CFCs were used as refrigerants back in the mid-1900s, and the release of them into the atmosphere proved to be really harmful. Solar radiation can cleave the bonds of carbon and a halogen, and then the halogen radical can deplete ozone in the stratosphere through radical chain propagation. Since the Montreal Protocol in the 80s and the stop to CFC use, we've seen a lot of improvements to the ozone hole.
As for a fun fact about one of the elements contained within the halogen group, you may have noticed that we have not discussed astatine a lot in this discussion about the halogens, and it is considered a halogen because it is in group 17. However, there's not a lot known about astatine in general and about its reactivity, and in particular, its reactivity is not similar to the other halogens discussed. However, different isotopes of astatine have actually been investigated as a potential cancer treatment. And the one I'm focusing on today is 211 astatine. And this is because the astatine 211 isotope actually emits an alpha particle during its nuclear decay. And this alpha particle, and in general, alpha particles are known to kill cancerous cells. But what makes 211 astatine a particularly attractive cancer treatment is the fact that its alpha particle has an optimal half-life. So not only will it be effective once injected into the body in killing a cancerous cell, but it also will not remain in the body long enough to kill other healthy tissues. This is actually more advantageous to other compounds such as bismuth or polonium because it has a relatively short half-life, around 7.5 hours, so it will not remain in the body for long. So not only will it not remain in the body for the sake of not killing healthy tissue, but also will not really remain in the body for a long period of time, so as not to pose a biotoxicology risk to the patient. However, it should be noted that due to the fact that astatine and the different complexes that can be formed, an example of which is one I've shown on the right here, have been limited in the study of their stability and the implementation to test these in human subjects.